Okay, all right. Welcome back, everybody. So, yesterday we ended with a discussion of some boundary value problems for the heat equation. So, let me just bring those back. So, for now, I'm going to label these just 1, 2, and 3. Okay, so the examples were as follows. So say that we consider like heat flow. So the quantity in question is temperature considered as a quantity measuring heat, right? So U of xt is temperature at position x and time t. Now instead of doing this on say all of r and t positive, this is on some finite length thin metal bar with ends arranged at x equals 0 and x equals L. This is the 1D heat equation that should govern this situation. So there are a few different types of BVPs we considered. One is inhomogeneous Dirichlet. So it's inhomogeneous because these boundary conditions here at the boundary could be whatever temperature. It could be T naught at the left end and T1 at the right end. Those two things could be different potentially. So this is inhomogeneous Dirichlet. It's Dirichlet just like in the wave equation. So this is Dirichlet because this is a condition on the temperature itself. This is a condition on the value of the solution itself at the ends. This is homogeneous Neumann. It's Neumann because this is now a condition on the x partial here, right? The flux of the heat flow out the ends. It's homogeneous because these are both 0. Okay, and of course mixed is, well, one is a Dirichlet condition, one is a condition on the value of the solution at one of the ends, and one is a condition on value of the partial, the x partial of the solution at one of the ends. So this is, these are 3 different types. This isn't the only thing. I'll talk very briefly about a Robin condition, what it means in this setting. But anyway, this is just kind of a smattering of different sorts of BVPs you could see for the heat equation. Okay. Now, it turns out that every single one of these is solvable via this method that we're going to be focusing kind of the last bit of the class on, which is separation of variables. So all of these can be solved via separation of variables. So we're going to see how each of these goes with separation of variables, and then, get directly from that some long-term behavior. But it turns out that, we should have an intuition for the long-term behavior of this anyway, right? We should actually have some intuition for what the long-term behavior of solutions to this should look like, or how they should behave. Even without this. This will, once we see the specific forms here that we're going to get out of this, this will kind of verify our intuition. But we actually should have some intuition about what these things should look like anyway. So in order to see that, so let us consider the long-term behavior of a solution. We'll say u of xt to each of 1, 2, and 3. Obviously not simultaneously, right? That wouldn't be too good. All right, so each of these. Of course, when I say long-term behavior, right, what is it that I actually am seeking here? Right, when I say long-term behavior, what do I mean? Well, this is like the eventual temperature distribution, right? So, i.e., what I want is the eventual temperature distribution, or another way of saying this is the steady state temperature distribution. Okay. I.e., if what we want is long term, right? We seek the behavior of the following quantity. We define v of x to be the limit as t goes to infinity of our solution. Then what does this thing do? This describes the distribution at infinity, right? So as t goes to infinity, this is what I mean by the long-term asymptotic eventual temperature distribution here. Okay, with respect to t. Okay. And so let's suppose, right, that this is indeed the thing that uh, I'm interested in. Let's look at this for this third equation first. All right, so consider 3 first. What is happening here? So in this case, one of the ends is attached to my giant room that has constant temperature T naught, or my giant universe with constant temperature T naught. Okay. And the other end is insulated. Right? There's no heat that escapes, right? Because this x partial at the L end is 0. So no heat escapes this end, and this end is attached to a universe having constant temperature T naught. Okay. You can think of, in this context, this initial g of x as providing an initial temperature distribution, right? So this g of x is like an initial temperature distribution. My left end is at a constant temperature T naught, right? It's attached to some universe, constant temperature T naught. My right end is insulated, so no heat is escaping. Okay. So what is going to happen, right? Regardless of what the particular initial temperature distribution is, right, as t goes to infinity, what should happen to this bar is, like, intuitively, right? Intuitively, the temperature in this entire bar should approach what? It should approach this T naught, because this end is insulated, this end is T naught. So regardless of what this initial distribution is, as t goes to infinity, since this is always, since this is being kept constant for all t, right, then the temperature in the entire bar should equilibrate, right, to this T naught temperature, right? And so in this case, what should happen is that v of x should be identically the constant T naught. That's my intuition, right? So to verify this, we'll have to wait until we solve these with separation of variables. But this is my intuition. This is kind of if my equation is governing heat flow in the way that I think it does, this is how things should go, right? If I've set up this situation properly. Okay. All right. What about the second one, where both ends are insulated? So let's consider number 2. Both ends are insulated. consider 2. In this case, both ends are insulated. What does that mean, right, in terms of what's going on? So I have heat equation. Both ends are insulated here in this metal bar. And I have some initial temperature distribution, right, g of x. So what should happen is what? Well, my idea is that we know that these lateral sides are insulated. The ends are insulated. I have an initial temperature distribution. So then on the whole bar, what should happen? What should happen is that the temperature in the bar should equilibrate to like the average of this temperature distribution G, right? In fact, what happens, so in this case, the temperature in the bar should equilibrate to the average temperature of the initial temperature distribution. In fact, what are we saying is that we expect this v of x to be equal to 1 over L times the integral from 0 to L of g of x dx. Now maybe at first, like more loosely, you just expect it to equilibrate to like some temperature, right? But if you think about it for a second, what should that temperature be? Right, recall here we're not given some initial temperature distribution at one of the ends, right? We're only told that the ends are insulated. Well, it turns out that that temperature it equilibrates to should be the average of the temperature distribution, or the initial temperature distribution. So if that is, if that's a little bit confusing, then just wait. Right? Soon enough, we'll have full justification for this when we actually have an explicit form of the solution in front of us. Okay. So then, what about the last one? So what about the last one, number 1? So here is the Dirichlet condition. I have different temperatures at the end, so you could think about this bar being attached to different universes, right, that all have constant constant temperature T0, T1. There's no addition or loss of heat, basically from the initial temperature distribution. Once T goes from 0 to anything positive, instantly, right, at the ends, we have T0 and T1. Okay. And those universes it's exposed to don't gain or lose heat in this way, right? So it's just instantly T0, instantly T1. Okay. So in this case, what is it that happens, right? Let's consider one. Well, in this case, we could say, well, what if the two initial temperatures are equal? Right? So what if at both ends, actually, it's the same temperature? What would we expect would happen in this bar? Well, we would just like in the first case, we'd expect that eventually this would equilibrate to the outside, right? So eventually the heat would equilibrate to the outside. i.e. this steady state solution would just be identically the constant T0, which is the same as the constant T1, right? It would be that. Okay. If these two are not equal, however, right, there's some temperature gradient. All right, we'll see after separation of variables that this v of x will be T0 plus T1 minus T0 times x over L. And I want to check something, right? This thing at 0 is T0, and this thing at L is T1. Right, so note that if I define v in this way, then this is a linear function. All right, so this is a linear function that has ends T0 and T1. So it's T0 at the left end and T1 at the right end. Okay. Now you might think about why that would make sense, but we'll have to wait until we talk about separation of variables to actually see where this comes from. Okay. All right, so then we'll be back to verify that this is indeed how things go later once we have the tools. So you might say, oh, you skip straight to finite, right? Finite intervals in considering these problems. You skip straight to finite intervals, and you didn't do like a semi-infinite interval, right? For like a semi-infinite bar, a bar with one end and then it's infinite in the other direction, right? Instead of like an infinite bar. If you think, well, it turns out that if you want to do the semi-infinite case, you can proceed basically how we did with the wave equation as far as reflections go, right? You can proceed like that to deal with a Dirichlet boundary condition, we'll say, at one of the ends of a semi-infinite bar. You can use our normal solution formula for the 1D heat equation. You can use that on the whole real line, except apply it now to like the reflected problem, right? So take the initial data, your initial temperature distribution on the semi-infinite line, do an odd reflection, and then the formula on the whole real line for that varied problem gives you what you want. Okay. So a quick word about the Robin condition. So quick word on Robin condition for 1D heat equation. So what is a Robin condition? So this is just like before. It's a combination of Neumann and Dirichlet. So here's an example. Maybe it's something like this, right? So we'll say at x equals 0 at the left end, we have for all positive t, C1 u of, of 0. Yeah, let me rewrite this. So C1 u of 0t plus u sub x 0t is equal to C2 where C1 and C2 are some constants. So for some constants, C1 and C2. All right, so it was clear what like the interpretation of these boundary conditions were physically for Dirichlet and Neumann. So Dirichlet is telling me the like temperature, right, of the, so this is telling me like the value of the solution at the ends, right, which in this case is temperature at the ends. Here this is telling me the change, right, in temperature, the change in the heat at the ends. So that's Dirichlet and Neumann. What about the Robin condition? What is this saying, since it's a combination of the two? What is the idea here? So in the Dirichlet case, we said, oh, well, you know, this, we were considering like attaching the bar like at its ends to these giant rooms or universes that had constant temperature T0 and T1, and then after some time T that's positive, right after this initial time, instantly the ends became these temperatures, right? And there was no addition or loss of heat from that process. Here in the Neumann, right, there's no loss of heat out of the ends, for instance. Well, if we allow for heat transfer, right, then we get something like this showing up. So how does this work? All right, so imagine now, of course, this is a single Robin condition. There would be another one, say, maybe at the other end. So this is at the left end, right? So imagine now we attach the left end to some reservoir, some medium, so air, liquid, whatever, with temperature, with temp, we'll say T0. Okay, but we expect a transfer of heat between the left end of the bar and the reservoir, right? But now we expect a transfer of heat between the left end of the bar and the reservoir. So this is left end of the bar is x equals 0, and the reservoir that it's attached to. Okay. Well, how does this work? So this transfer of heat works by Newton's law of cooling, we'll say, is a model for this. What does Newton's law of cooling say? It says that this temperature flux at the left end is proportional to the difference between the temperature of the bar at that end and the ambient temperature of its surroundings. Right? So temp flux at left end this is proportional to the difference between the temperature at that end and the ambient temperature of the surroundings. Is proportional to difference between the temp of the bar at x equals 0, which is, of course, this temp. Right, it's my Dirichlet condition. Right, and the ambient temperature of its surroundings. Of course, we'll say for the purpose of this that this reservoir has, we'll say this reservoir has temp T naught. So its surroundings, this ambient temp is like T naught. In this case, rewriting Newton's law of cooling in words here, or rather, rewriting these words from Newton's law of cooling in math language, right? This would say that this temperature flux at this n is proportional, so it's some constant times T naught, that ambient temperature, minus the temperature at the end. But if we're in a situation, so here, C1 and T naught are constants. So if we are in a situation described by this, it turns out that actually these two things are really like the same sort of condition. In fact, we even have, as far as the sign here goes, right? So let's see how this works, that we've oriented this properly. If T naught is bigger than the temperature at the end of the bar, then this is, say, positive, right? So if both C1 and T naught, of course, if we take both of these to be positive, if this one's bigger than this, then this heat flow is going to be positive, so it's going to flow to the right. Okay, otherwise it's going to flow to the left. So this is telling us whether it's flowing into the bar or out into the reservoir, right? So our intuition checks out that all of this works and all of this makes sense. So one interpretation of the Robin condition is exactly in terms of this, right? I'm allowing I'm allowing heat flow from the bar into the reservoir, the room it's attached to. Okay. All right. Now, on to what's probably the last very important property of solutions to the heat equation, which is the maximum principle on a finite interval. So the maximum principle on a finite interval. So what does this say? Now, you might say that we already have a maximum principle, right, for the 1D heat equation on the entire real line. So recall, we already have seen, this is actually one of our big properties of the solution to the heat equation. So we've already seen that we have a maximum principle for the IVP, that is, u sub t is alpha u sub xx on r cross 0 to infinity, and u of x0 is g of x on r. So we already have a maximum principle for this. What did that maximum principle say? It said that basically the value of the solution, right, was never greater than the max value of that initial distribution, the initial data, right? So this max value at time t equals 0 actually provided a max value for the value of the solution on that entire domain, right? So that's nice. That's certainly a nice fact. But it turns out we can say more if we restrict our attention to a finite interval. So actually, we can say more by restricting our attention to a finite interval. Now, you you may actually, you may kind of think here that, actually, this is kind of funny, because if you know a little bit about, some very basic topology, very basic analysis plus topology, you'll know that, well, of course, if I move from this very much non-compact region to a region that is, so I've basically replaced R with a finite interval now, and if I really wanted to, talking about a finite interval for t as well, then I've replaced the domain that I'm interested in, which is not compact, right, with something that's going to be compact. And in terms of finding maximums, right, maximums, minimums, those sorts of things, having a compact set that I'm dealing with in question is definitely the thing that I want, because that is the thing that guarantees existence of a lot of these sorts of things, right? You can go back and do this for just basic like Calc 1 type stuff, where having just a continuous function on a closed interval. Right? So having a continuous function on, say, a closed and bounded interval, right? A compact set in R, gives you automatically a max and a min. Okay, this is a version of like the like the basically the max min theorem, right? So this is something that you get just because the set, it's a continuous function on compact set, is a nice object in terms of those things. So that's one way of kind of thinking about this, but I'm not actually going to go into the proof, but the proof essentially just relies on basically some of those same basic calculus facts, and a little bit of a trick in the computation. But what is it that what's the setup for this maximum principle? Okay, you might immediately say, wait, why is moving to a finite interval going to tell us more? Usually when you talk about a finite interval, now I need boundary conditions here, and it seems like that complicates things. So it turns out that for the purposes of a maximum principle, the actual boundary conditions at these points don't matter. Okay, so all we need is for our u of xt to solve the heat equation. So we need it to solve the heat equation for x in the open interval, so the interior of this finite interval, and t greater than 0. Okay. So in order to state this, what do I want to say? So first, let's fix big T positive and define omega sub t to be the following domain. It's 0L cross 0 to t. What does this look like? Well, here's 0. Here's L. If this is the xt plane, right? Here's x. Here's x. Here's t. Here's big T, we'll say. And so in the xt plane, this is just the rectangle with its boundary here is omega t. Now I can think about this as two parts, of course. So this omega t is really like the inside of omega t, right? The interior of omega t, which I'll write like this. So it's everything inside this rectangle together with, right, union with the boundary of omega t, which maybe I can indicate with this red pen, right? It's just the boundary rectangle. It's not what's inside, it's just the boundary rectangle. Okay. Now, let S, the way to remember what S is for sides, right? Say sides without top. That's what the S stands for. So let S be, if I actually write out what this is, right, it is the, so let S be the sides of omega t minus the top. Minus the top side. So if I drew a picture of this, this would be, so here's big T, here's 0, here's L. S is going to be the left side, the bottom side, and the right side. None of the interior points and not the top. This set is what S is. Okay. Of course, if I actually wanted to write this out mathematically, what is S? S is going to be, it's going to be the bottom, right? So here's, it's the set of points that look like x0 for x between 0 and L. So this is the bottom. Union the left side, so that's points that look like 0t, right, where t is between 0 and big T. So this is the left side. And then the right side. So these are points LT, where t is between 0 and big T. So this is the right side. Okay. Now, what is the maximum principle? So this is my theorem. Let u of xt be a smooth function on omega sub t, which solves the diffusion equation. U sub t equals alpha u sub xx. For alpha, some positive constant as always. For x strictly between 0 and L, and t strictly between 0 and big T. Then the maximum of this solution over S is actually equal to the maximum of the solution over omega sub t. So what does this say in words, right? It says that the maximum of my solution over this entire region, which is interior points and the sides, is actually obtained somewhere on this union of the three sides. So this maximum happens here, somewhere here, at some point on this set. So it doesn't happen in the interior and it doesn't happen on the top. Okay. Now, there's stronger versions of the maximum principle if we're willing to be really careful with our assumptions, but for us, this is all we're going to need. Okay. So I'm not going to prove this. If you're interested in a proof of this fact, it actually, once you see the calculational trick, if you could actually understand these quantities, like if these partial derivatives were defined for you, technically the machinery that proves this is Calc 1 type stuff. So Calc 1 is pretty much all you need to understand the proof. So this proof is on pages 297 and 98. So again, what does this say? So this says that the maximum value of u over this finite domain, omega t, must occur either at the initial time at t equals 0 or at the boundary points, right? X equals 0 or x equals L. So that's where the maximum has to happen. Of course, you are immediately familiar with this for other sorts of analogous statements that you can make about functions more generally on a domain, right? But here, notice that we weren't able to just say, oh, like you might say, how is this any different than me seeking maxima and minima on just a compact region more generally, right? Well, normally, let's say you just have some generic function defined over some compact two-dimensional region like this. What would you be able to say? You'd be able to say that, okay, we'll say that it's smooth, right? So it's definitely continuous. So it has a max and a min, and that max or min can happen where, right? If this thing is smooth, you'd have to say something like, well, it can happen either somewhere on the boundary, in the one-dimensional case at the endpoints, right? Or at a critical point in the interior. So if it happens in the interior, it can't just happen at any old point. It would have to happen at a critical point, right? This is one of our consequences of, this is like Calc 3 type second partials test stuff, right? So when you have some, say, function of x and t defined over a two-dimensional region like this, and it's smooth, without knowing that it solves any kind of differential equation whatsoever, you could say, well, if it has a max and min, and that max and min happens either somewhere on the boundary, in which case maybe I have to use like Lagrange multipliers or something, right? Or it happens somewhere in the interior at a critical point. But here, notice, like, this is a stronger statement because this isn't just a completely generic function of x and t. This is a function of x and t that solves the diffusion equation. And so somehow that tells me actually that maximum can't happen in the interior. And there's a version of this that would say the maximum can't happen in the interior unless the function is just constant over that domain in question. So it's like my maximum can't happen in the interior, well, unless use constant on the corresponding domain. Okay, so it happens somewhere on the boundary, but actually it happens specifically at one of these parts of the boundary, right? And so somehow the fact that this solves the diffusion equation is telling us that it's restricting our attention to where it has to happen, either at initial time t equals 0 here, right, at the bottom, or on the sides, right, at the x equals 0, x equals L ends. That's where the maximum has to happen. Now, a couple of things to note. So note, firstly, if we replace u with minus u, we can obtain the minimum principal. So if you like, there's not just a maximum principal, there's also a minimum principal, arguing in the exact same way, just by replacing u with minus u. So that's one thing. Question, what is a nice application or consequence of the maximum principal? The answer is that it provides an easy way. And one of these will be one of your upcoming homework problems. It provides an easy way to prove uniqueness and stability of the BVP, IVP, given by any of the, we'll call them 1 through 3, since I had previously called them that. Let me find my sheet so I don't have to write any of them again. All of these examples of boundary value problems, you can prove uniqueness and stability for each of those using the maximum principle, and it's almost immediate. It requires very little argumentation. This will do it. Okay. I will show a similar argument for Laplace's equation later if you're curious as to what the reasoning is. But recall kind of your first step, right? Whenever you're trying to prove uniqueness, right? Kind of like the thing you always do is you're trying to prove uniqueness, which is that there is at most one solution, right? So that, for instance, if you were to have two solutions, right, two distinct solutions, then somehow this is a contradiction. Somehow, actually, those two solutions that you thought were distinct have to be the same solution. So typically, the way to do this, especially for these linear problems, is to assume you have two solutions to one of these IVPs, and then look at the difference of the solutions, right? Say, okay, well, what if we considered the difference of the solutions, right? What IVP would that thing satisfy? It would satisfy some similar but slightly different IVP, right, where the boundary conditions would change in some way that I'm sure you can figure out. And then the question becomes, well, what is the solution? What is the solution to that IVP? And using the maximum principle, it can be shown, of course, that that solution must be identically 0, so that those two functions have to be identically equal to one another. That's the basic reasoning. Okay, but that's how this is used. So the maximum principle is the thing that is used to show that that solution needs to be 0. Okay, the solution to this modified BVP. So all of these can have uniqueness, and stability is actually not hard at all also to show using the maximum principle. So a consequence of the maximum principle is that uniqueness and stability can be shown for any of those boundary value problems. Okay, one more thing about the heat equation. So one more thing. So let's go back to Duhamel's principle. Now, Duhamel's principle was essentially unmotivated when I when I covered it for the wave equation. Um, Unfortunately, I'm not going to, at least not in this video, I'm not going to uh, give like a full rundown of kind of a physical interpretation of Duhamel's principle or why this works, why we should expect this to work. I'll show you where in the textbook this is referred to, but you know, we're more interested in some other things, but this is still useful to see how this also works for the heat equation. So just like for the wave equation, we can introduce a source term. So consider a heat equation IVP with a source term. So we have the heat equation. We'll move all of the heat equation stuff to the left side. So this is u sub t minus alpha u sub xx is equal to some source term, this function little f of xt, and this is for x in RT greater than 0. And we have some initial temperature distribution g of x. Okay. So it turns out that the explicit solution is given by the following. U of xt is my homogeneous part, right? If we're getting flashbacks to ODE days, the homogeneous part would be the integral from minus infinity to infinity of my heat kernel convoluted with the initial data. So this is the term that solves the associated homogeneous portion where this f is 0, right? Plus my inhomogeneous term, if you like. This is the integral from 0 to t, the integral from minus infinity to infinity of f of y s phi of x minus y t minus s dy ds. So the variables that I'm integrating with respect to here are y and s. So you can verify that this indeed solves the heat equation, but you're going to have to use some of these properties of the fact that, you know, phi converges to the delta distribution at this singularity, right, when t is 0. But this can be shown to solve this IVP. Okay. And so you can actually do this just with the Fourier transform. So Fourier transform will get you there on its own. But this can also be done, so this can be done via Duhamel's principle, as we did in the wave equation. So what was Duhamel's principle? Duhamel's principle takes this IVP and splits it up into two different IVPs, where for one of them, the source term has been incorporated into the initial data somehow. Now, an explanation for why you could possibly be able to incorporate this source term into the initial data. I'm not going to go through all of those details. It takes a few pages in the textbook to do so, but I'll tell you where that happens. Okay. And so, let us rewrite. So how do I do Duhamel's principle for this thing? So I seek a solution to the IVP that is, I have zeroed out the initial condition. So I seek a solution to this thing. And I apologize if you can hear vacuuming out in the hallway. They're vacuuming the hallway of my apartment. And I happen to lecture on the bar near the door, so you might be able to hear that. And I apologize if that's the case. So I've zeroed out my initial data. So I seek a solution to this IVP. Okay. And what I do now is, once I've found it, I simply add it to my usual solution to the IVP for the associated homogeneous problem, which is the normal heat equation, right? So U sub T minus alpha U sub xx is equal to 0, and U sub x0 is equal to g of x, right? So if I have a solution to this, which I know, I can write that out in terms of the heat kernel. The heat kernel convoluted with the initial data gives me a solution to this. Okay, then if I know a solution to this IVP, all I have to do to get the solution to this thing is add them together. This is principle of superposition. It works because this is a linear equation, right? So that is the only reason that works. Okay, but then the question is, how do I solve this thing? Let's call this smiley face. Okay, how do I solve smiley face? What do I do? All right, so to solve smiley face, I introduce a parameter s, right? And this parameter s is between 0 and infinity. And for each fixed s, I solve the following IVP for, we called it in the wave equation, we called it W. We'll solve this for Wxt parameterized by S here. So what does this become? So this is W sub t of xt s minus alpha W sub xx of xt s is equal to 0. So now this is homogeneous. Okay, and I know how to handle that. But now my initial condition is replaced with the source term. Okay, and of course, a solution to this is given immediately by my usual convolution formula to be W xts is the initial data convoluted with the heat kernel, right? But now, how does this work? This is the integral from minus infinity to infinity of f of y s phi of x minus y t minus s dy. And so Duhamel's principle would say that I take this, which is going to solve my smiley face, I add it to the solution, which is my usual 1D heat equation, IVP, and I should get the solution to this. Well, that process I described gives exactly this formula. Right? Okay. You might say, wait, this has a single integral, right? This is not an integral from 0 to t, so that integral from 0 to t is obtained by the u of xt, that solution to this thing is obtained by integrating this, right? So that's what Duhamel's principle says. So the solution, I should maybe rephrase that. The solution to smiley face is obtained by integrating this from 0 to t, okay, with respect to this parameter s. So solution to smiley face, u of xt is the integral from 0 to t of w of xt s ds. Okay, you can call that like a short version of Duhamel's principle. Okay. Now, why does this work? Right? Why does this work? I.e., what is the physical explanation for why I can do this? So what is the physical explanation for why I can incorporate the source term into the initial data in this subproblem? So for an answer to that, you're going to have to look at, so this is 299 to 302 in the textbook. If you want to see an answer as to why you can expect this to work, or why maybe this does work, this is kind of probably the best quick explanation. Now that explanation only applies to the heat equation, but it turns out that if you're careful, you can use similar reasoning to show why Duhamel's principle could be applied to the wave equation just as well. And so that's that. This is but one way of dealing with IVP with source term, and it's useful. This is a useful trick to have in your tool belt. Okay, that is the last that I wanted to say concerning the heat equation. And so before we move on to separation of variables and return to all three of these second order equations we've been talking about now for so long, well, we're not going to talk about this last equation for super long so that we can move on to what we're really interested in. And in a weird way, this last equation is going to be, in a strange way, more complicated, even though that doesn't seem like that should be the case. And in some instances, not the case, but, well, we'll get to that. One more thing here so that I stop rambling. One more thing before moving on to separation of variables. For all of the big three. Well, it's called the big three because there's three of these equations, and we've only talked about two of them so far. We've talked about the wave equation and the heat equation, right? So it's time to talk about Laplace's equation. So this is the contents of chapter 8 in the textbook. Okay, so Laplace's equation. What is it? So we've already mentioned it previously, many lectures ago when I was giving examples of the big three. So Laplace's equation is the following. Recall that the Laplacian of u in dimensions, right? So in, say, in big N dimensions the Laplacian of u was defined to be the pure second order partial with respect to each of the variables summed so this is the Laplacian of u, which you've already dealt with a little bit, right? Your midterm had you computing the derivative of total energy for the higher dimensional, three-dimensional wave equation, which involves the Laplacian. That's, all of these. So, technically, every single one of these equations we've seen so far of second order have involved the Laplacian, right? So the wave equation, right-hand side is the Laplacian. Diffusion equation, right-hand side is the Laplacian. And Laplace's equation definitely involves the Laplacian. And you could say that's all it involves. A couple of course interpretations here. Laplacian of u is the same thing as the divergence of the gradient of u. If you view u as, so in 2D, if I view u as a function of, say, just x and y, then Laplacian of u is u sub xx plus u sub yy. In 3D, of course, Laplacian of u is u sub xx plus u sub yy plus u sub zz. If u is some generic function of n variables, what's the Hessian of u? The Hessian of u is the matrix of mixed second order partials, right? So a matrix of second order partials. If u is even remotely a reasonable function, i.e. the second order partials all commute, so it doesn't matter what order you do them in, you might notice that this is a symmetric matrix, right? So the Hessian is nice. So this is a symmetric matrix, this is a square matrix. And actually, these are the diagonal terms of this matrix. So another way of thinking about this is that this is the trace of the Hessian matrix of u, right? If you really like. Because of writing the Laplacian of u as divergence of the gradient, and because physicists are in love with writing the divergence of a vector field as nabla dot f, of course, this is nice suggestive notation, because if you've forgotten what the divergence of a vector field is, this reminds you, because it says, oh, if I treat this gradient operator as the thing that it's a vector, right, containing the partial operators in each of the corresponding slot, then dotting those with the components, or with f, thought of as being made up of the component functions, right, f's a vector field, then what you get is exactly a scalar valued thing, exactly denoted by this. That's what the divergence is. So thinking of it this way, you can think of this as nabla dot the gradient of u, and so physicists like to write the Laplacian as like nabla squared u, because it's suggestive notation as to what's going on. In every mathematical treatment, you're going to see this. You're going to see this delta used instead. So this is what I'm going to use. Okay, but just know that if you open up a textbook or a paper that is more interested in physical physical applications of this, or comes from physical setting primarily, you might see this oftentimes. That's fine, right? Doesn't matter. Okay, so this is my Laplacian of u. So then, what is Laplace's equation? Laplace's equation is in some, spatial dimensions, right, n, is saying that that n-dimensional Laplacian of u is equal to 0. Okay. Now, this, of course, is a very special thing. In fact, a function u, so quick definition, a function u that satisfies Laplace's equations, or Laplace's equation, okay, is called harmonic. And the study of such functions could be called harmonic analysis, right? Now, it's impossible for me to oversell how nice and how important harmonic functions are in a variety of applications. So there's nothing I could say that would be too extreme for saying how nice these things are. If you've had Math 463, you will have already encountered them a little bit. Harmonic functions show their head in complex analysis, but they show their head in a lot more places than that. So I think here's a good stopping point before I say too much more about Laplace's equation. We are basically going to finish our treatment of Laplace's equation in like one-ish lecture. And the reason for that is because we have a few properties that we want to say that are very important and kind of, I mean, in a way, they're actually equivalent to solving Laplace's equation. So saying my function has one of these properties, so the mean value property, for instance, if I'll define what that is in tomorrow's lecture, and it turns out if you have a function that satisfies the mean value property, then you know it satisfies Laplace's equation. So we'll talk about all those things. The reason why the treatment of Laplace's equation is so short is in order to write out the types of formulas that I want to for Laplace's equation, just like I did for the wave equation and the heat equation, in a way it takes a little bit more work, and that seems kind of weird because this equation, right? If we just say what takes the most writing, right? This or like the the wave equation or the heat equation. Well, like look, this doesn't even, there is no t. These are all purely spatial, right, things going on here. So in a sense, like this equation has simpler structure, right? But we'll see how that's not really for the purposes of us wanting to write out these explicit formula, it's actually going to be a little bit more involved. We are going to return to it if we have time after separation of variables. But basically, we are going to be able to write out fundamental solutions, but seeing exactly how those fundamental solutions generate the explicit solution formulas that we seek, that takes a little bit more work. And so we're not going to do that on our first pass through. On our first pass through, we're going to note some properties that these things have, and we're going to be happy to leave it there for a bit. And then we'll, like I said, we'll return to this after we do separation of variables. So we'll pretty much cover everything that we're going to talk about in chapter 8 in like one-ish lecture, and then we're going to start maybe not tomorrow's lecture, but the lecture after, we should start on our march through separation of variables material so that we can start doing some of these computations involving the big three for these boundary value problems. So finally, we're going to be able to address these things, go all the way back to the wave equation. The wave equation, you remember how complicated the boundary value problems were, right? All of these, the domain of dependence and influence is very complicated, right? You had all these reflections going on. It was complicated stuff. We're going to see how to actually write out explicit solution formula in those cases in a way that's not so bad, in a way that's very straightforward and is entirely mechanical. So it will take us back a little bit to the ODE days when being asked on an exam or a quiz or homework or something to solve an ODE was this mechanical process, right? You kind of went through this almost like a flow chart of what you're dealing with for the ODE in question, and you had a process for writing out explicit solutions. So we're going to have a process similar to that in spirit via separation of variables. So anyway, that's the plan. That's where we're headed. So that's all for today. I will see you all next time. You're going to have homework posted relatively soon. If not today, then tomorrow. It will be a couple of explicit calculations and some calculations you've seen. Well, you've seen very, very similar stuff previously, and these will involve the heat equation. It may be like one on Laplace's equation, but nothing too fancy. Just kind of verifying some basic properties, as I mentioned previously. But anyway, that's that. So I will see you all tomorrow.